Alright, so recall from the previous lecture that we were trying to define what a morphism of varieties is. Okay, so we have a pair of varieties, two varieties, they could be either affine or quasi-affine varieties, and then we want to say when a map between them is a morphism of varieties. Okay, and we use the analogy that I gave you in the last lecture, namely the analogy from the topological spaces. Okay, so if x and y are topological spaces and f is a continuous map of topological spaces, of course you know that a continuous map pulls back continuous maps to continuous maps. That's just a restatement of the fact that a composition of continuous maps is continuous. But the more beautiful thing is that if you have a set theoretic map that pulls back continuous maps to continuous maps, then it follows that that set theoretic map is itself continuous. The proof is deceptively simple, and you could say more or less tautological, but this is the importance is with the philosophy that you define a morphism as a map which pulls back good functions to good functions. So let me make this definition of what a morphism between varieties should be. So here we go, let x and y be varieties. By a morphism from x to y, phi from x to y, we mean a continuous map phi from x to y such that for every open subset V in y, the pullback map, the pullback of functions of regular functions, I should say the pullback of maps via phi takes regular functions on V, namely OV, to regular functions on U, namely OU. So the diagram is like this: here is x, here is y, here is phi, and here is the open subset and open subset V. Of course, whenever I say open subset, it's of course non-empty. Okay, and in all these situations we are not going to look at the case when the open subsets are empty, because we don't want to define regular functions on an empty open set. Okay, so so of course I should tell you that where u is actually f inverse v. Okay, so here is v and here is u, which is f inverse v, and this is also open. That's because phi is a continuous map. Of course x and y are varieties, so they have the Zariski topology. Therefore you know what open sets mean, and you take an open set here. The inverse image of an open set is an open set, because and I should use not f, I have messed up the notation. It should be phi inverse here, it should be phi inverse there as well. Okay, and I have this map from phi inverse v to v. Now this map from phi inverse v to v will give you a map from OV to OU. And what is this map from OV to OU? What is an element of OV? It's a regular function on V. Okay, an element of OV is a regular function on V. So what is a regular function on V? It is a map from V to K. A regular function on V is a map from V to K, which as we had defined in the earlier lectures, is a function which is locally given by quotients of polynomials, where the polynomials are considered in the right number of variables in which v or y is the right number of variables, which is equal to the dimension of the affine space in which v or y is sitting inside. Okay, so well, here is v and here is phi. This is u. So u takes phi, phi takes u to v, and then the pullback will be this map. You pull back essentially means composition. So this is first apply phi, then apply f, and this is called as phi upper star of f. So this is f going to phi upper star of f, the pullback of f, which is by definition first applying phi and then following it up by f. Okay, so so this is the requirement. The requirement is you take an open subset of the target variety, take a regular function on that. If you compose it with phi, you should get a regular function on the source. Okay, this is the condition. This is just the condition that the map phi is continuous and it pulls back regular functions to regular functions. Okay, this is the definition of what a morphism is. What you must understand is the following, that if you go down from the category of varieties to the category of topological spaces, that is, you forget the variety structure and just look at all these things as the underlying topological spaces with the, of course, with the Zariski topology, then what will happen is, if you give me a continuous map, if you give me a morphism phi, of course phi is continuous, and if you give me a v and if you give me a regular function on v, this f is of course going to be continuous, because I have already proved to you that regular functions are continuous. Okay, a regular function from a variety is always a continuous map, continuous with the target k being thought of as a1 with the Zariski topology. This is something that we proved last time. Okay, so since phi is continuous and f is continuous, it is very clear that f circle phi, which is the pullback of f by pullback of f by phi, which is also phi upper star f, it's clear that this is continuous. Okay, but what our requirement is that it's not just a continuous map from u to k for the Zariski topology, it should actually be a regular function from u to k for the Zariski topology. That is the requirement. Okay, so that is what has to be singled out. Okay, so the moral of the story is a continuous map such that if you take a regular function on the target, on an open subset of the target, and take the composition, okay, what you get on the source, a subset of the on the right subset of the source, is not just a continuous function. It has to be more. It has to be itself a regular function, namely it has to be locally given by quotients of polynomials. That is the requirement. Okay, so it is a philosophy that it's a map of varieties is a map which is continuous and which pulls back good functions to good functions, and the good functions here are regular functions. Okay, now so here is the the point I want to make is the following. So here is a nice little theorem. The theorem is, if you look at if you take a variety x and look at all the possible morphisms into A1, you will get exactly all the regular functions on x. Okay, so morphisms of varieties from x to A1 is naturally isomorphic to O x. Okay, so the regular functions are actually morphisms into A1. There is no difference. Okay, what are elements of OX? They are maps into A1, which is just K with the Zariski topology, alright, and which are locally given as quotients of polynomials. That's what a regular function on X means. Okay, and what is a morphism of varieties from X to A1? It's also a map from X to A1, which is a map from X to K, but then the condition is that it has to be continuous and it should pull back regular functions to regular functions. Okay, and the beautiful thing is that there is no difference between a regular function and a morphism into A1. So regular functions are exactly the same as morphisms into A1. Okay, so let me write that. That is, regular functions are, so in fact I should not even put isomorphic, I should put equal to, are morphisms into A1. So of course it is A1K, where K is the fixed algebraically closed field over which we are working. Okay, so it's a very nice theorem. It says, it tells you that your morphisms into A1 are the same as regular functions into A1. Okay, so let's try to prove this. So so what you do is, so what is a map? Of course this map is, it's the identity map. Okay, it's the identity map, but the only thing is that when you take a regular function on X, the target is taken as K, and the target K, you don't care about the topology on the target K, but if you put a topology on the target K and call it A1, then you know a regular function is continuous. So it's certainly a continuous map from X to A1, but the fact is it's actually a morphism from X into A1. Okay, that's what this theorem says. So let's prove this. Let phi from X to A1 be a morphism. Okay, what do I have to show? I have to show that phi is a regular function. Alright, now so this means phi upper star from O of V to O of phi inverse of V for any open set V inside A1. Okay, so if what is a morphism? A morphism is a map which is continuous and it pulls back regular functions. So if you give me an open set in the target, which is an open subset of A1, then and you give me a regular function on that open set on A1, which is an element of OV, then applying phi upper star, the pullback should give me a regular function on phi inverse V. Okay, now what I am going to do is this way is actually very easy. You put V equal to A1 itself. Put V equal to A1. Okay, then you get phi upper star will go from O of A1 to O of X. Okay, because phi inverse of A1 is X, the inverse image of the target space under any map is the whole source space, okay. I will get this, okay. And then what you, and then we will use the fact that in on O of A1, see I have the identity map. See, the identity map on A1 is a regular function on A1. See, the identity map on A1 is a map that sends every point of A1 to its every point of A1, namely every point of K to itself. And what is it? O of A1, if you want, is A of A1, the ring of functions on A1, which is Kx, okay. And what does the identity map correspond to? It corresponds to the polynomial x. Identity map corresponds to the polynomial x. The polynomial x evaluated at lambda gives you lambda, okay. So O of A1 is the same as A of A1, okay. That is something that we have already seen. O and A coincide for affine varieties, alright. So O of A1 is same as A of A1, and identity map in O of A1 is actually that corresponds to the function defined by the polynomial x, okay. So this is so identity map is certainly a regular function. Identity map on A1 is certainly a regular function, and what does it go to? It will go to phi upper star of the identity map on A1, but phi upper star of the identity map on A1 is just phi. Phi upper star of the identity map on A1 is identity map on A1 composition with phi, which is just phi. And but then you are saying that this is here, so you are just saying that phi is in Ox. So this will tell you phi belongs to Ox. So it's very clear that a morphism from X to A1 is certainly an element of Ox, okay. So phi as an element of morphism, phi as a morphism of varieties from X to A1 is certainly also in Ox, right. So this is very trivial, alright. I have to now do things the other way around. I will have to say that I have to start with a regular function, and I will have to start with a regular function on X and say that that is a morphism, okay. So let me do the other way. Conversely, start with an f in Ox, okay. Start with an f in Ox, right. I want to show that f is actually a morphism into A1. So my f in Ox means that f is a regular function defined on X, its target is K, and we have already seen that if this target K is given the Zariski topology and is thought of as A1, then this f is of course continuous, okay. We have already seen that regular functions are continuous. So that means that f from X to A1 is continuous. So what are the two defining conditions for a morphism? It should be a continuous map, and then it should pull back regular functions to regular functions. So we will have to check for every open set V in A1 and every psi in OV, f upper star psi, which is just psi f followed by psi, is in O of f inverse V, okay. This is what you will have to check. You have to check that it pulls back regular functions to regular functions, right. So now you see what you must understand is that V is an open subset of A1, and of course I'm certainly not looking at empty sets, alright. So you know a non-empty open subset of A1 is actually a basic open set, okay, because you see what you must understand is the open sets in A1 are complements of finitely many points, okay, and therefore they are complements of finitely many points, and there is always a polynomial with roots exactly at those points, and it's the 0 set of that polynomial which is the complement of this open set, and therefore this open set is defined as the basic affine open set given by the non-vanishing of that polynomial, okay, that polynomial which vanishes at those points in the complement of the open set. You must understand that the important fact we are using is that A1 has the only closed sets in A1 are finitely many points, and this is basically commutative algebraic reflection of the, it's a reflection, geometric reflection of the commutative algebraic fact that every ideal in the polynomial ring in one variable over a field is generated by a single element, okay, it's a PID, right. So so the fact is that let V be D of G, okay, where G is an element of if you want A of A1, which is identified with Kx. G is a polynomial in one variable, right, and V is D of G, it's a basic affine open defined by G, right. Then then what is O of V? Then O of V will be O of dg, and what is O of dg? Our definition as we have checked, it's just Kx localized at G, okay. The regular functions on dg are the same as the A of dg, and that's defined to be the localization by G, okay. So O of V is just this, okay, and so what's an element of O of V of the form, it's of the form some h by G power m, where m is a positive non-negative integer, okay. An element of OV looks like h by G power m, alright. This is how an element in the localization looks like, and you are thinking of this h by G power m as a function on as a regular function on V, and every regular function on V looks like that, right. And now if you, so let me draw this diagram. So I have x, I have A1, and here is f, and here is D of h, okay, which is my V, and then I have f inverse V. This is open, of course f is a regular function, it's continuous, so the inverse image of an open set is open, so f inverse V is open, and then I have on D of h I have a regular function, okay, and that regular function is given by h by G power m. This is an element of O of D of h, and then I compose it with f to get the pullback. This is a regular function into k, okay. Sorry, this is D of G, it should be D of G, I'm sorry, it should be D of G. I think I have messed it, did I mess it up somewhere there? No, I didn't, okay, I messed it up here, alright, it should be D of G, right. So yeah, so I have h by G to the m, which is a regular function on dg, and then I compose this to get the pullback function, which is f upper star of h by G power m, which is by definition equal to first apply h and then apply first apply f and then apply h by G power m, and so it's going to be well, so if you calculate it is actually f's h circle f by h circle G to the m. This is what it is, okay. So because this is what it will be when you evaluate it. If you take an x here, then it will go to fx, and when you evaluate h by g power on m on fx, you will get h of fx by g to the m fx. So effectively this is h circle f by h circle g to the whole to the m, alright. And here of course and now the point is that what do I have to check? I have to check that this is a regular function on f inverse v. I have to check that this is a regular function on f inverse v, okay. So is something wrong? Oh sorry, this is g, sorry you are right, it is g circle, okay, it is g circle, oops, yes, g circle f to the n, right, yes, yeah please check that, it is f followed by h divided by f followed by g whole to the n, yeah, thank you, yeah. So so I will have to check that this is a regular function. I mean if you think about it for a moment, you will not hesitate to realize that this is a regular function, okay. But then if you want the way to look at it is the following. The way to look at it is that you see the locus, see f is a, see so let's look at what f is. So f is a regular function on x, okay. So you know I want to say the following thing. I just want to say that if I tell you that h circle f is a regular function on f inverse v, and g circle f to the m is also a regular function on f inverse v that does not vanish on f inverse v, then the quotient will also be a regular function on f inverse v. I am just using the following thing, I am using the following thing, namely that suppose you have a regular function that does not vanish, then its reciprocal will also be a regular function, because the only condition for a regular function is that it is locally given by a quotient of polynomials, and if that quotient of polynomials does not vanish, it means that the numerator polynomial does not vanish if they are in the if there are no common factors, and if the numerator polynomial does not vanish, then the reciprocal of the quotient is also a valid quotient of polynomials, and that tells you that the reciprocal of a regular function that does not vanish is also a regular function, alright. So therefore if I claim, therefore it is very clear that it is enough to show that h circle f is a regular function, it is enough to show that h circle f is a regular function on f inverse v, g circle f is also a regular function on f inverse v, and g circle f does not vanish on f inverse v, okay. It is very clear that g circle f cannot vanish on f inverse v, because if g circle f vanished at a point on f inverse v, it will mean that at the image of that point under f, g will vanish, but then the image of that point is supposed to lie in dg where g cannot vanish. So it is very clear that g circle f cannot vanish on f inverse v. So the only thing therefore I have to prove is that h circle f or g circle f are actually regular functions, okay. But so let me write that down. It is enough to show that h circle f and g circle f are regular functions on f inverse v, okay. This is all I will have to show, okay. Now this is again something that is very easy to see, because you see the f I started with was a regular function on x. So f is given by a quotient of polynomials in the right number of variables, the number of variables being the dimension of the affine space in which x sits, alright. So f is locally a quotient of polynomials, okay. So h circle f will also be a quotient of polynomials, the same number of variables, because h is just a polynomial in one variable. When I take a polynomial in one variable, and substitute for that variable another polynomial in some m variables, the resulting thing will again be a polynomial in m variables. It is obvious. Therefore the moral of the story is that it is very clear that since f is locally a quotient of polynomials, H circle f is locally a quotient of polynomials on x, okay, then H circle f is also locally a quotient of polynomials on x, okay. So let me write that down. This is obvious for locally f is equal to p by q, where p comma q are polynomials in the right number of variables, which is a of an with x sitting inside an, okay, and you know, and if h is equal to h of x is equal to sigma ai x to the I equal to 1 to say some t, then H circle f is locally h of p by q, which is sigma I equal to 1 to t ai p power I by q power I, okay, which is a polynomial in k of x1 etc xn divided by some power of q. So you are done. So the moral of the story is that if you really think about it, it is very clear that a regular function is also a morphism. So there is no difference between regular functions on a variety and morphisms into A1, there is absolutely no difference, okay. So the beautiful thing is that to define a morphism we started with regular functions and then found that regular functions are themselves special cases of morphisms, okay, and that in that sense it should not be very surprising. But you must understand that, you see, right from the beginning this is again you know amplifying more and more the philosophy of Felix Klein, that you know the geometry of the space is completely controlled by the functions you choose on it. So you know we started with affine space, we started with the n dimensional space Kn, we chose the functions to be polynomials. Using the polynomials we defined the Zariski topology on Kn, okay, and then from the Zariski topology we started translating back into commutative algebra, and we came down to defining we first came down to guessing what should be regular functions, okay, for example on basic open sets, and then generally what should be regular function, what the regular function should be on a general open set, okay. And then after we defined regular functions, once we defined regular functions we found that if you take affine varieties, the regular functions are just polynomials, okay. And we also found that using these regular functions we could define morphisms, and then it is not surprising that finally regular functions themselves turn out to be morphisms, okay. Alright, so that's a very nice thing, it's a very nice result. But now what I am going to do is that I am going to say that this statement here is only it's still a special case of a very general statement, okay. So let me make that statement. So so again let's look at that statement, morphisms of varieties. So this is morphism in the category of varieties from X to A1. is identified with Ox, okay, and you know and I just want to say that this is isomorphic to homomorphisms of k-algebras from A of A1, which can be identified with kx, to Ox. Okay, so you see now what I'm trying to do is I'm now trying to translate things. See, on this side the morphisms I have is in the category of varieties. Now I want to go, this is geometric part, this is geometric side. I want to go to the commutative algebra side and I want to translate morphisms of varieties into morphisms of rings, in this case morphisms of k-algebras, and this is the way I do it. What I do is I think of Ox as being I interpret it as being bijected to the set of all k-algebra homomorphisms from the A of A1, which is kx to Ox. See, you know, there is this universal property of the polynomial ring in one variable, which says that a k-algebra homomorphism from a polynomial ring in one variable is completely dictated by the image of the variable x. Okay, so any k-algebra homomorphism from kx to Ox, from kx to any ring, is simply controlled by what you are sending x to. So more generally, so let me recall universal property of kx of Rx, okay, where of course R is a commutative ring with 1. What is the universal property? The universal property is that if B is, if A is any R algebra, then A home R algebras from Rx to A can be identified with A by simply sending a map F from Rx to A to Fx, to the element Fx of A, because it is a substitution, right. It all sending a map from Rx to something means that you are substituting x for something in every polynomial in X with coefficients in R. So it completely is controlled by what you are substituting x with. If you substitute x with some lambda, then you have to substitute every polynomial in X with x in place, with lambda in place of x. So it is controlled by that. This is the universal property, and in fact this universal property is also valid in several variables. More generally, homomorphism as R algebras from R x1 through xn to A is isomorphic to A to the n, where you simply send a map F from R x1 through xn to A to the tuple fx1 dot 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 fxn to the n tuple. That is a map, an R algebra homomorphism from a polynomial ring in n variables is dictated by the images of those variables. These statements are restatement of the universal property of the polynomial ring over a given ring. Okay, so and I am just applying, instead of R I have put the field k, and instead of A I have put Ox. So the homomorphism from k algebras from kx to Ox is just Ox, and that is what this is. Okay, and now let me tell you how this statement generalizes. The statement generalizes like this. Okay, it's very beautiful. So it generalizes like this: morphisms from X to A1 can be identified with homomorphisms of k algebras from A of A1 to OX, okay, and morphisms from X to AN can be identified with homomorphisms of k algebras from A of AN to OX, okay, and morphisms from X to Y, okay, where Y is affine, okay. So instead of taking the target to be A1, I can take the target to be AN. Instead of taking the target to be AN, I can take the target to be an affine variety. So the morphisms from any variety into an affine variety can be identified with homomorphisms of k algebras from the affine coordinate ring of that affine variety to OX. Sorry, this should be Y. And mind you, this AY is the same as OY. There is no difference because Y is affine. And in particular, you see, in particular, if X is affine, the last statement says that the morphisms, so here of course these are all morphisms as varieties. On this side it's the geometric side, there are morphisms between geometric objects, and this side is the algebra side, the commutative algebra side. So the morphisms of varieties from X to Y can be identified with homomorphisms of k algebras from AY to AX, and mind you, I can replace OX by AX because OX and AX are the same because X is an affine variety, okay. So this is the these are the two important statements, this one and this one. And why are these statements important? These statements we will prove these statements, okay, and they are just generalized versions of this first statement, which is just the simple statement that the regular functions on variety are the same as morphisms into A1, okay. It's just a generalization, it's a grand generalization of that, but how grand it is that it actually gives you an equivalence between the category of affine varieties and the category of finitely generated k algebras. That is the reason why this is a very important statement. So you have category, category, so let me do that in the next board so that I have a little bit more space to write down what I want to write down. So what I do is now I can really complete the picture that I gave several lectures ago, and then I was just throwing statements at you. So here is on this side I take the category of affine varieties, okay, and here the objects are affine varieties, namely irreducible closed subsets of AN for some n positive. These are the objects in the category, and I am going from there to the category of finitely generated k algebras that are integral domains. Sometimes instead of writing so much, people just say the category of affine coordinate, the category of affine rings over K. The affine rings means they are actually rings of functions on affine varieties. Okay, so and abstractly they defined as finitely generated K algebras that are integral domains, which means that you are just taking a finite, you are just taking a polynomial ring in finitely many variables over K and going modulo a prime ideal, so that you get an integral domain. Okay, and you know I have this, I have a functor that takes objects to objects here. So what it does is that if you give me an x, it takes this x to, well, a of x. Okay, so it takes x to a of x, and it takes an to a of an, and it takes this closed immersion to a quotient. Okay, and you know what that map is? If you call this closed inclusion as I x, you know what this map is? This is just I x star. You can check that this map, the inclusion map, is actually a morphism of varieties, and you can check that the pullback I x star that it induces from the O of this to the O of this, which is the same as the A of this to the A of this, is simply the restriction. You can check that. Okay, so this Ix gives you this Ix star. Okay, and what are the morphisms? The morphisms here are, well, if you have x and y to affine varieties, I get you have a morphism f, then that will give rise to a map on this side that will go the other direction. So it will go from ay to ax, and you know what that is? That is just f star, it's the pullback. So the fact is that if you give me a morphism of varieties, the pullback map is actually a ring homomorphism. Okay, that's something that you can very easily check. It's obvious, and in fact it's a k-algebra homomorphism. So the morphisms on this side are k-algebra homomorphisms. They are ring homomorphisms which take one to one and which respect the vector space structure. They are k-linear, so they are k-algebra homomorphisms. And the fact is that this is the functor. Now A is a functor. It's a functor because it goes, not only does it associate an object to an object, but it associates a morphism to a morphism. Okay, to every morphism varieties you get a associated k-algebra homomorphism. So this is the functor, and the fact is that this is an equivalence of categories. This is an equivalence of categories because there is an inverse functor which as I told you is given by max spec. The max spec functor, starting with a finitely generated k-algebra A, I can look at max spec A, that's a variety, okay, that can be identified with a variety. And if you give me a k-algebra homomorphism G phi from A to B, then what you will get is you will get a from the max spec to the max spec, you will get a homomorphism in the reverse direction, namely max spec phi, and this is just pull back of given a prime ideal in B, given a prime ideal in B, the inverse image of the prime ideal will be a prime ideal in A. And the fact is you can check that because these are finitely generated k algebras which are integral domains and K is an algebraically closed field, if you take a maximal ideal in B and you pull it back, you will get a maximal ideal in A, and so it will take max spec to max spec, and this is the inverse functor. And these two functors are inverses of each other in the sense that you start with an object, you go there and come back, what you get is an isomorphic object. Okay, and then similarly if you start there, you go here and come back, you will get something that's, you will get an isomorphic k-algebra. So if you start from here and go and come back, you will get an isomorphic variety. If you start from there with an algebra, go and come back, you will get an isomorphic k-algebra. Okay, and that's why these two functors are called inverse functors, and we say that each of them defines an equivalence between the geometric side, which is the category of affine varieties, and the commutative algebraic side, which is the category of finitely generated k-algebras, which are integral domains. And you know, it's easy, but and certainly not an exaggeration to say that this is the full-blown form of the Hilbert nullstellensatz. Okay, with all the other definitions in the right place, this is the grandest form of Hilbert's nullstellensatz. Okay, so with that I'll stop this lecture.